In this video, we're going to study power series. Now, to really understand what we're doing here with power series, let's remind ourselves of the geometric series. So, a geometric series, right, is one that looks like this. Or, if we'd like, we could start it at n equals 0. And change the exponent to n instead of n minus 1, right? The point is it should start with an exponent of 0. And we know that under the right conditions, this sums up to a over 1 minus r. And those conditions would be that the absolute value of r needs to be less than 1. So that's what we know about geometric series. So a power series is just me replacing r with x, essentially. So and also I'll just, for simplicity, let a be 1 and r be x. And if you do that, then you have this series here, which then by the same reasoning would give you this 1 over 1 minus x. Now, because x is a variable, what we're doing now is we're able to say that this power series is equal to this function. So we can now think of functions that are themselves infinite series. All right. So let's take a look at an example here. So what are we going to do with this? It says use the facts above to find the power series representation of this function g of x. So in other words, we're going to rewrite functions so that they are represented as an infinite series. All right, so let's take this g of x, which is equal to 3 over 2 minus x squared. And what we're going to try to do is make it look just like this, right? So we're using this fact in the background that under the right conditions, this infinite series equals this. So we're trying to make this form pop up. So we first might look at it and say, okay, well, what's different about these? Well, for one, the 3 in the numerator shouldn't be there. So let's pull the 3 out so that now I just have a 1 in the numerator. And then we want a 1 here instead of a 2, so let's also pull a 2 out. And that's fine as long as we understand that as this 2 distributes back through, it's got to give me x squared again, so I'll say minus 1/2 x squared, right? So that when I take 2 times that, I get this back again. And so now what I have is I have this 3/2 times 1 over 1 minus, and then I'm going to put this in parentheses, 1/2 x squared in parentheses. And so that is becoming my x. So you can see that you're going to take in this simpler form, you take the x, and that is the base of your exponent that you're raising to the n power. So now what I'm going to do is I'm just going to take this entire thing and raise it all to the nth power. So here's how that's going to look. I'll still have my 3/2, but now instead of all this, I write the sum from n equals 0 up to infinity of 1/2 x squared, all raised to the n power. And I can do a little bit of simplifying here, right? So this will be 3/2, n equals 0 up to infinity. And so I can distribute that exponent through, 1 to the n, 2 to the n, and then x squared to the n. And of course, 1 to the n is just always going to be 1. and then 2 to the n. And then, of course, this is going to be x to the 2n. So I can put all this together then, and I can say that g of x is equal to the infinite series n equals 0 to infinity of x to the 2n over 2 to the n. Now there is one catch, right? So this original equality up here we know is only true when x, or the absolute value of x, is less than 1. So what we're going to need is for the part that became our x, so this part right here, we are going to need to ensure that the absolute value of that is also less than 1. But of course, the only part of this that could be negative is the x, so I'm going to go ahead and do this, which means the absolute value of x squared is less than 2, so the absolute value of x is less than the square root of 2, which of course means that x is somewhere between negative root 2 and root 2. So I can say this is the case, g of x equals this, but I also need to make sure that I add on that x has to be between negative root 2 and root 2. So understand that what we're saying here is that this infinite series can basically be used instead of this formula here. Now I think what will be helpful is if we take a look at this situation in the graphing calculator. And in order to do so, what I think we'll do is we'll calculate, maybe the first 4 or 5 terms of this thing. So let me say it this way. G of x is approximately going to be equal to 3/2 times, and then let's start plugging values of n in. So if I plug n equals 0 in, then of course we get 1. If I plug in, so here's n equals 0, n equals 1. So if I plug in 1, I'm going to get x squared over 2. And then if I plug in 2, I'll get x to the 4th over 4. And then x to the 6th over 8. And of course we can keep going, right? Dot, dot, dot. But let's go ahead and just stop here. So it's the first 4 terms. So what I'm going to do is in my calculator, I'm going to put this in for one graph, and then I'm going to put this in for the other graph. So just bear with me here. All right. So let's see. I think that's the same function that I did earlier, but oh well, I guess I already got rid of it. So 3 over 1 minus x squared is my function. Excuse me, 2 minus x squared, not 1. 2 minus x squared. And then let's type out the first 4 terms of this series. So it's 3/2 times 1 plus x squared over 2 plus x to the 4th over 4 plus x to the 6th over 8. And I think that's where we decided to stop. So it's just a partial sum. But this shows what's happening quite nicely. So if I go to my graph, the blue is the original function. The red are the first 4 terms of my infinite series. So notice how good of a job even just the first 4 terms of the series is doing of replicating the function. And in fact, if you look at the x values that it's doing a good job with, it looks like, here's the square root of 2, negative square root of 2, and square root of 2. So in that region, it's doing an okay job, right? So we have the interval of convergence here, and the more terms I use, the closer the red is going to hug the blue. But notice outside of that interval, the red's nowhere to be seen. Okay, so that's what that interval of convergence really means in this case. All right, so let's take a look at another example. Actually, before we take a look at another concrete example, let's kind of set ourselves up for that example. So the other thing that we want to be able to do is basically do calculus on these power series. So what this theorem says is that if you have a power series, and by the way, if you have x minus a, that's just a more general version of the power series. The last one we did was x minus 0. But if you have a power series like this, then and you have a radius of convergence for that power series, then the function that is defined by that power series can be differentiated and integrated. So what you can do is literally take the derivative term by term, or you can go ahead and look at the formula and just take the derivative. So notice down here, how do you take the derivative of something to the power of n? You multiply by n down here, right? And then you take 1 away from the exponent. And you can go through and do that term by term as well. Of course, the constant term out front, when it's x minus a to the 0, you take the derivative of that, it's 0, so it's gone. c1 times x, take the derivative of that, you get c1. And so you can see the derivative rules playing out here. And similarly, you can take the antiderivative, or the indefinite integral. So you can just raise everything to the next higher power, the n plus 1 power, divide by n plus 1. Just remember also to do a plus c if it happens to be an indefinite integral. And then the other really important part here is that the radii of convergence of the derivative, or the integral, is going to be the same radius of convergence of your original power series. All right, so in this example, we're going to see how this idea of taking a derivative can be really quite helpful to us. So we have this function 1 over the quantity 1 minus 3x to the second power. Now, we have used this template to kind of figure out how to write functions that have an x squared in them as a power series, but it's a little bit different matter when we have the entire quantity squared. That's a little bit further from looking like this. So we might ask ourselves, how do we get from something that looks like this to something that has a square in the denominator? And so what I would have you remember here is that in Calc 1, if I asked you to take the derivative of 1 over x, right, you would probably bring the x up and raise it to the negative 1, and then it would be negative 1 x to the negative 2, which would give you negative 1 over x squared. And so there is a way that you got from something in the bottom of your fraction raised to the first power to something that's something raised to the second power. So what I suggest we do here is let's start with coming up with a power series for this, and then maybe using differentiation to transform it into something that looks more like this. So the power series for this, right, just means that instead of x, it's 3x, so 3x is being raised to the nth power. So I could say 1 over 1 minus 3x is n equals 0 to infinity of 3 to the n, x to the n. But this is not true all the time. It's only true for certain x values. So of course what we need is for our 3x here, for its absolute value to be less than 1, which means 3x is between negative 1 and 1, which tells us that x has to be between negative 1/3 and 1/3 in order for this equality to hold. Okay, but that's our interval of convergence, right? So that's okay. So now what we can do is say, can I take the derivative of both sides of this equation? And come up with something that looks like g of x on the left. And the idea is, whatever it is that happens to the right by doing the same process would be the power series for that that function g of x, if we can produce it on the left side. All right, so the derivative on the left side here, right, probably going to start by getting it ready by raising it to the -1. I'm just going to rewrite this. All right, and then moving down a little bit here. So on the left side, we know how to take that derivative. So that is going to be -1 times 1 minus 3x to the -2 power times the derivative of the inside, right? Don't forget the chain rule. So times -3. And then that's supposed to be equal to the derivative of this, okay? Now, one of the things that is really important here, if we go back to our previous page, notice that we're starting off with a summation from n equals 0 to infinity, but then our derivative is just from 1 to infinity, okay? That's an important step, and so you can apply the derivative power rule just to the formula itself and write that down, and that's fine as long as you remember to change n to 1. Now let's talk about why that's the case, and to kind of help us understand it, what I'm going to do is this. I'm going to say I'm going to take the derivative of, I'm going to write out my n equals 0 term. Okay, so my n equals 0 term is 3 to the 0, x to the 0. So my n equals 0 term is 1. And then I'm going to write everything else. Right? That's completely fine to do, right? Just take the very first one and write it out separately. So we have to understand that when we do take the derivative of 1, it becomes 0. It goes away. And so that's why when you apply the derivative formula over here, you want to start it at n equals 1 instead. And so bring the n down, 3 to the n, and then x to the n minus 1. And then over on the other side here, -1 times 3 is 3, and then 1 minus 3x squared. So now what we have to do is compare this to what we ultimately wanted, right? So what we wanted was 1 over 1 minus 3x squared, and we have 3 over 1 minus 3x squared. Well, that's really no problem. We can definitely deal with that. So let's just multiply both sides by a third. So now the left side looks exactly like the function that I wanted. And then here, I could distribute my 3 through if I wanted to. N equals 1 to infinity of n times, there's a 3 to the 1 on bottom, so we subtract the exponents, so times 3 to the n minus 1 times x to the n minus 1. Now, one thing I just want to point out to you is that you might see a couple different types of answers in a scenario like this. So don't be alarmed if when you look up the formula, look up an answer for one of the things you're doing, you might see this, which is exactly what we have written already. And of course, we're going to write our interval of convergence right there. So x needs to be between negative a third and a third. But just don't be thrown off if when you look up your answer, maybe it's something like this. Just understand that this is the exact same answer. So if you want to, so what's the point, right? The point is you start with a 1 here and a 0 here and a 0 here. Well, if you put 0 as your first, then if you start with 0 plus 1, 0, 0, then that gives you the exact same series. So there's different representations for the same thing. So just don't be alarmed if you see different representations of it. All right, so now let's look at another example here. And in this example, what we're going to do is try to come up with, oh, sorry, that was the same page twice. Here's the example we actually want to do. So what we're going to do here is we're going to come up with a power series for the natural log of 1 minus 3x. Okay, now that looks nothing like this form here. Okay, but here's the thing we should think about. In Calc 1, or excuse me, Calc 2, what would we have to do to something like 1 over x to produce the natural log of x? Right? The thing we would have to do is take the antiderivative. Right? That would equal our constant plus the natural log of x. So what we'll do is similar strategy to last time. We'll try to come up with something that looks more like this and then see if we can integrate our way to producing the function that they want from us. All right, so I'm going to start with the same one. And the beauty of that is that I don't have to do any more work. So just based on the work we did in our previous example, we can already say that this is n equals 0 to infinity of 3 to the n, x to the n, and x needs to be between negative a third and a third. All right, now let's apply the integral to both sides. All right, now the hard work's going to be over here on the left side. All right, so you might think for a minute about what it is that you would do to actually perform this integration. And hopefully pretty quickly you come up with the idea that, hey, I know what to do with the integral of 1 over x, so let's make it look more like that. So let's let u equal 1 minus 3x. So that would mean du equals negative 3 dx. So du over negative 3 is my dx. Okay. So down here, I can go ahead and say this is one over u du over negative 3. Okay, and what's that equal to? Well, over here, we know that all we have to do is remember that there's a constant that comes about when you integrate, but then from there, it's just n equals 0 to infinity of 1 added in the power and then dividing by that n plus 1. So there's our formula already there. And then here, we get negative 1/3 natural log of u is going to be equal to this. And then we, of course, have to plug back in what our u is, right? So this will be negative 1/3 natural log of 1 minus 3x. Now, I'm going to drop my absolute values here, which, you should, in general, be careful about doing. But the reason I'm dropping my absolute values is because I know that x has to be between negative 1/3 and 1/3 anyway, right? Because that's the interval of convergence. And all those values will always give me a positive number inside of this natural logarithm. So there's no way it could ever be positive. So, I could keep the absolute values there, but I'm wanting it to match exactly the original, which had no absolute values. All right, so what's the difference between h of x and what we've got? Well, just that negative 1/3, right? So what I can do then is multiply both sides by negative 3. All right, and then let's think about what's going to happen here. Changing my color back. So this is going to be the natural log of 1 minus 3x. Now, okay, it's going to be negative 3c. Okay, but negative 3c is just another constant. So I'm going to be kind of lazy about this, right? And I don't care, negative 3 times c. Yeah, I'm going to distribute it through, but it's a different one. It's d. Okay. But then that changes all this to a minus, right? This is going to be minus 3 times the sum from 0 to infinity of 3 to the n, x to the n plus 1 over n plus 1. And then furthermore, I have this factor of 3 out here, so it might really be nice to go ahead and bring that into the fold. And so we've got the natural log of 1 minus 3x equals d, minus, bringing that 3 in gives me 3 to the n plus 1, x to the n plus 1, all over n plus 1. Now, while this is correct, and if you did this on a test, I would not be upset leaving it as n equals 0 to infinity. But if you see n plus 1s everywhere, and you're starting at 0, it sure is much more elegant if you can get rid of all those n plus 1s and say, okay, I'll just make everything n, and I'll just start it at 1 instead. Right? So that would be kind of the preferred way of showing that. And then finally, what about this d? Okay, what are we supposed to do with that? Well, what we could do is we could plug in a value of x for d. So for example, if you plugged in the natural log, let me kind of do this as an aside here. So plug in x equals 0 to find d. So the natural log of 1 minus 3 times 0 equals d, right? Because if you plug 0 into all these terms, everything's 0. So that's kind of nice. But then what do we get? The natural log of 1 equals d. But guess what? The natural log of 1 is 0. So in this case, d is 0. So that leads us to h of x, which is equal to the natural log of 1 minus 3x, is equal to the opposite of this infinite series right here. All right, so the last example that we want to take a look at here is kind of a cool example. We're going to approximate this integral, and the deal with this integral is that it's not one that you're going to be successful at integrating, with use substitution or any of your other techniques that you learn in Calc 2. So now, of course, you learn some numerical methods in Calc 2 that'll help you out. Simpson's rule, the trapezoid rule, the midpoint rule, those kinds of things. And those are great, but here's another way that we can go at this. If I can express that particular integrand as a power series, then I can integrate term by term. So that's what we're going to try to do, is we're going to say, what can we do with x squared over 1 plus x to the 6th? All right, so taking a look at what we've got here, this is going to be, well, what do we want to do, right? We want to continue to emulate this. Right? So we want to make it in this form. So step 1 for me is to say, well, I don't want x squared up on top, I want a 1. Okay, fine, so let's factor it out. And then on bottom, I'm okay with weird stuff happening in this term, but I definitely need a minus sign. So, anytime you have plus something, you can always make it minus just by going minus negative, right? And so what we have here is that this part is going to be our x. So I'll have x squared is equal to the sum from n equals 0 to infinity of negative x to the 6th raised to the nth power. Now, when we do something like this, and we have a negative in there, remember that you can always rewrite it as negative 1 times x to the 6th to the nth power, which then could be rewritten as negative 1 to the n times x to the 6th n. All right, and then I could do a little bit better. I could bring my x squared back into all these terms. So this becomes n equals 0 to infinity, negative 1 to the n times x to the 6n plus 2, right? Adding the exponents when we have like bases. All right, so of course we do need to make sure that we understand our interval of convergence. They are asking us to integrate from 0 to a half, so hopefully that's within our interval of convergence. So of course what's going on here is we're saying the absolute value of negative x to the 6th needs to be less than 1, which means that the absolute value of x to the 6th is less than 1, which means the absolute value of x is less than the 6th root of 1, which is still 1, right? And then x is between 1 and negative 1. So there's our interval of convergence, and so that's good because 0 to 1/2 is within it. All right, so now we can just add that. So what we have here is that x squared over 1 plus x to the 6th is equal to this as long as x happens to be between negative 1 and 1. But now we can answer their question, right? So their question was, what is the integral from 0 to a half of x squared over 1 plus x to the 6th dx? All right, well, we now know that that's going to be equal to the integral of 0 to 1/2 of this infinite series. And we know how to come up with a formula for that. So this is going to be equal to the integral from 0 to a half or not the integral, excuse me, we're taking the integral right now. It's going to be equal to the sum from 0 to infinity of, so we're going to go through and we're going to add 1 to the exponent, so 6n plus 3 instead, all divided by 6n plus 3. And under normal circumstances, we would go plus c, but we're not going to do that, right? Because we know exactly what numbers we want to evaluate at. So plugging those in, we end up with the sum from n equals 0 to infinity of -1 to the n over 6n plus 3, and then we're going to times by a half to the 6n plus 3. And then, of course, plugging 0 in all of these places is of course going to give you 0, so we don't need to bother to write it. But if this was something other than 0, then of course we would subtract, right, our values using the fundamental theorem of calculus there. So this is where we're at here. So now they asked us way at the top to estimate this within 10 to the -6. So we want that estimate. And the thing that we should take note of right away is that this is an alternating series. So remember, with alternating series, we continue to add and subtract until we get terms that have a size that's smaller than the desired error, and then we keep all the terms that came before that. So let's start plugging in values of n. So for n equals 0, we would get 1 over 3 times 1/2 to the third. Then if you let n be 1, you're going to subtract 1 over 9 times 1/2 to the 9th. And now as I'm going, I'm going to kind of keep track of how big these are approximately. So this is 0.0417. This one is 0.000217. So this is small, but definitely not smaller than this. So I keep going. Plus 1/15 times 1/2 to the 15th. And that's getting pretty small. 5 zeros and then a 2. But that's still bigger than this, right? Because this is 5 zeros and a 1. So I'm betting that this next one's going to be smaller than that, but we'll go ahead and write it out. And when I make that calculation, it's definitely less, and I forgot to write it down, so excuse me. I'll do it right now. So this is going to be 0.00000002. So this is smaller than that. So that means we don't use this one, right? We use all the ones that came before it. And so just taking these first 3 terms only, what we should get here as an answer is about 0.04145 17, we'll call it.